Dear students, in this class let us discuss about some interesting results regarding the convergence of a sequence. So let x equals sequence xn be a sequence of positive real numbers. It's a positive reals such that L equals limit xn plus 1 by xn exists. Xn plus 1 by xn that exists. Then if if L less than 1, what is L? L is the limit of xn plus 1 by xn. If L less than 1, then the sequence xn converges. Then sequence xn converges and limit xn equals 0. This is an interesting result. What is xn? Xn be a sequence of positive reals. And what is L? L is the limit of xn plus 1 by xn. Then if L less than 1, then the sequence xn converges. So the sequence converges only when L equals, only when limit xn plus 1 by xn less than 1. Okay. If L less than 1, the sequence xn converges and limit xn equals 0. How to prove this one? So its proof is in this way. What is sequence xn? Sequence xn is the sequence of positive reals. When xn greater than 0, then what about limit xn? Limit xn also greater than 0. Then xn greater than 0 for all n falling. Since xn greater than 0, what about xn plus 1? Xn plus 1 is also greater than 0 for all n falling n. Why? Because it is a sequence of positive reals. So that means this is xn plus 1 by xn. Xn plus 1 by xn also greater than 0. Then by the well-known result, we know that the for limit of xn plus 1 by xn, that should be greater than 0. That means L greater than 0. What is L? L is nothing but limit of xn plus 1 by xn. Clearly this L greater than 0. So now, suppose if L less than 1, come to the second part. If L less than 1, but L greater than 0, that means 0 less than L less than 1. Okay. 0 less than L less than 1. So you can choose an R such that this 0 less than L less than R less than 1. You can choose, or since 0 less than L less than 1, there exists an R such that this R lies in between where this L and 1. 0 less than, L less than, R less than 1. So you can choose R in such a way that this R lies in between L and 1. Okay. Now L less than R. L less than R means what is R minus L? R minus L is positive. Why? Because L less than R. So R minus L is positive. Put epsilon equals R minus L. Put epsilon equals R minus L. Clearly it is positive. R minus L, which is positive. Agreed? But we know that L is limit of this one. L equals limit of xn plus 1 by xn. That means for all epsilon is positive, instead of epsilon, here it is R minus L. There exists some k following n such that modulus of this xn plus 1 by xn minus L strictly less than epsilon. For all epsilon is positive and for all n greater than or equals k. Okay. So that means L minus epsilon less than xn plus 1 by xn less than L plus epsilon. From here. Okay. Minus epsilon, one step is skipping there. Minus epsilon less than xn plus 1 by xn minus L less than epsilon. You can add L, then you have Then we have L minus epsilon less than xn plus 1 by xn less than L plus epsilon. Come to the right side inequality. From here, epsilon equals r minus L. So what is L plus epsilon? From here, L plus epsilon is nothing but r. So from here, L plus epsilon equals r. Agreed? So that means we have xn plus 1 by xn strictly less than r for all n greater than or equals k. Okay, so that means this x you can replace, since it is true for every n greater than or equals k, you can replace this n by k itself. So it is xk plus 1 strictly less than r into xk. Xk plus 1 strictly less than or xn plus 1 less than r into xn. That is true for every n greater than or equals k. That means xk plus 1 strictly less than r into xk. Okay. So what about xk plus 2? Xk plus 2, according to, you can replace k by k plus 1. Why? Because it is true for every n greater than or equals k. So you can replace this k by k plus 1 here. What do you get? You have the next identity, that is rk plus 2 less than r into xk plus 2 less than r into xk plus 1. You can replace xk by or k by k plus 1. Okay. But what is xk plus 1? That is less than r into xk. So it is strictly less than r into xk. That means xk plus 2 strictly less than r square xk. Agreed? So what is xk plus 3? Xk plus 3 less than r cube into xk. Proceeding like this. So but what about rn? So it is proceeding like this. We have, sorry, not like rn, xn. Xn strictly less than r power xn strictly less than xk plus 3 less than r cube, xk plus 2 less than r square xk. So proceeding like this, we have xn less than r power n minus k into xk. Okay, that means that is xn less than, it is r power n into xk by r power k. R power n minus k, that is r power n by r power k. So it is finally xn strictly less than r power n into xk by r power k. What is xk? It is a sequence of positive reals. So xk is a positive real number. What is r? R is chosen, r is lies in between this 0 and 1. So since r is also positive, therefore r power k is positive. Why? Because k is a natural number. Then xk by rk is positive, r power k is positive. Then that means replace this xk by r to the power of k by some c. So clearly this c is also positive. You can replace xk by this r to the power of k by c. Why? Because c is any real, c is a real quantity. Then clearly this c is positive. Okay. So we have this xn less than r power n into c. Agree. So what is limit xn? Therefore limit xn equals c into limit r power n or limit r power n into c. What is r? R lies in between 0 and 1. So when n goes to infinity, then this r power n goes to 0. When n goes to, since r lies in between 0 and 1, r less than 1. So when n goes to infinity, the r power n goes to 0. Therefore, limit xn equals 0. That is what we require here. This is our requirement. Secant xn converges, such that and its limit is 0. So limit xn equals 0. Okay. So this is a very interesting research. Clear? Now, can you give an example for two sequences? Such as the two divergent two sequences are diverges, but their sum and product are converges. Suppose means that x equals secant xn and y equals secant y. These are two sequences. Suppose they are diverges. Both of these sequences are diverges. Such that the secant sum xy and the products xy are converges. Can you give an example for such sequences? That's an interesting question. It's a beautiful example. Why? Because consider this x equals 0, 1, 0, 1, 0, 1, etc. Surely this is a diverging sequence. Why? Because x converges to x goes to 0 as well as x goes to 1 means there are two different limits. Okay. What is y? Choose y as 1, 0, 1, 0, 1, 0, etc. Again, y is also divergent. Why? Because y goes to two limits. Y goes to 0 as well as y goes to 1. Clear? That is, the difference between two consecutive terms is always 1. Now what is xy or x plus y? Both are divergent. Why? Because these two sequences are converges to different points means they have two limits. So they are not converges means they are diverges. Okay. So what is x plus y? What? X plus y is 1, 1, 1, 1, etc. That's a constant sequence. Why? Because what is the range of the sequence? Range of 1, 1, 1. Its range. Its range is singletons to 1. So that's a constant sequence. So x plus y converges to where? 1. So clearly this x plus y converges. Even x and y are diverges. What is xy? xy is again 0, 0, 0, 0, etc. xy. Okay. Again this xy also converges. Here x plus y and xy are converges even though x and y are diverges. So this is an example for that. Clear?